Picture this: a star, millions of times larger than our Sun, suddenly detonates with unimaginable force. In less than a second, it unleashes more energy than our Sun will produce in its entire lifetime. This isn't science fiction. This is a supernova, the universe's grand finale for the most massive stars. But why does a star's death need to be so spectacular? What cosmic secrets are forged in these violent explosions? And could a supernova ever pose a threat to us here on Earth? Strap in, because we're about to journey into the heart of stellar destruction, where the death of one star becomes the birth of something extraordinary. By the time we're done, you'll see the night sky in a whole new light and understand how these explosions literally shape everything around us, from the gold in your jewelry to the air you breathe. This is the story of supernova, and it's far more incredible than you've ever imagined. Now let's break down exactly what makes a supernova so special in the cosmic scheme of things. A supernova isn't just any star explosion. It's the final, spectacular death cry of a truly massive star, packing more power than anything else we see in the universe. To put it in perspective, imagine our Sun suddenly exploding. Now multiply that energy by 100 billion times, and you're starting to grasp the sheer scale of a supernova. What's fascinating is how these explosions differ from their smaller cosmic cousins, like nova. While a nova involves a smaller star flaring up temporarily as it steals gas from a neighbor, a supernova marks the complete destruction of an entire star. And when we say these explosions are bright, we mean they can briefly outshine every single star in their host galaxy combined, visible across millions of light years. Think about that for a second. A single dying star in its final moments becomes so luminous that it can rival the collective light of hundreds of billions of other stars. That's the kind of cosmic fireworks we're talking about. But beyond the spectacle, these explosions serve a crucial purpose. They're the universe's way of recycling star material into something new, scattering the building blocks of planets and even life itself across the cosmos. To understand why some stars go out with a bang while others fade quietly, we need to look at their entire journey from birth to death. Picture a vast, swirling cloud of gas and dust in space known as a nebula. Over millions of years, gravity pulls these particles together, forming dense clumps that grow hotter and denser until nuclear fusion ignites at the core. That's the moment a star is born, lighting up the darkness with its own energy. Now, stars spend most of their lives in a delicate balancing act. The intense heat and pressure at their core fuse hydrogen into helium, releasing the energy that keeps them shining. But like all things, stars don't last forever. What happens next depends entirely on their size. Smaller stars like our Sun burn steadily for billions of years. When they finally run out of fuel, they gently puff away their outer layers, leaving behind a glowing ember called a white dwarf, a dense, Earth-sized remnant that slowly cools over eons. But for the real heavyweights of the cosmos, the story ends much more dramatically. Stars many times more massive than our Sun burn through their fuel at a furious pace, fusing heavier and heavier elements until they reach iron. Unlike lighter elements, iron doesn't release energy when fused, it sucks it up. That's the breaking point. With no outward pressure to counter gravity, the star's core collapses in a split second, triggering a cataclysmic explosion, a supernova. So while smaller stars fade into quiet retirement, the biggest ones go out in a blaze of glory, scattering their guts across the galaxy. And in that chaos, new elements are forged, new stars are born, and the cycle begins all over again. Now let's zoom in on one of the most spectacular ways a star can meet its end, the core collapse supernova. This is what happens when a true giant of the cosmos, a star at least 8 times more massive than our Sun, reaches the final act of its life. Inside these colossal stars, the fusion process is relentless. They start by burning hydrogen into helium, just like smaller stars, but their immense gravity means they don't stop there. Layer by layer, they fuse heavier elements, helium into carbon, carbon into oxygen, and so on, all the way up to silicon and finally iron. Here's where things take a dramatic turn. Iron is the star's downfall. Unlike lighter elements, fusing iron doesn't release energy, it absorbs it. So when the core fills with iron, it's like the star's engine suddenly stalls. Without the outward push of fusion to counteract gravity, the core collapses in less than a second. Imagine the entire core, a chunk of space the size of Earth but with the mass of our Sun, crushing inward at nearly a quarter the speed of light. The collapse is so violent that protons and electrons are forced together, turning into neutrons and releasing a flood of ghostly particles called neutrinos. Then, boom, the outer layers of the star, no longer supported by the core, come crashing down and rebound off this newly formed neutron core. The result: a shockwave so powerful it rips the star apart in a blinding explosion. For a brief moment, this single star can outshine its entire galaxy, scattering newly forged elements like gold, uranium, and platinum into space. And in the heart of the chaos, what's left behind is either an ultra-dense neutron star, or, if the original star was massive enough, a black hole. So while the star's life ends in a flash, its death creates the building blocks for new stars, planets, and even life itself. But not all supernovae are born from collapsing giants. Let's turn our attention to a completely different kind of cosmic explosion, the thermonuclear supernova, also known as Type Ia. These blasts don't come from massive stars meeting their doom. Instead, they involve a white dwarf, the dense leftover core of a smaller star like our Sun, playing a deadly game of cosmic theft. Here's how it works. A white dwarf in a binary system, meaning it's orbiting another star, slowly siphons material from its companion. Over time, the stolen gas piles onto the white dwarf's surface, increasing its mass. But there's a limit. Once the white dwarf reaches about 1.4 times the mass of our Sun, it crosses a critical threshold. The pressure and heat at its core become so extreme that carbon, the star's main fuel, ignites in an uncontrollable chain reaction. In a split second, the entire white dwarf detonates like a titanic stellar bomb. What makes Type Ia supernova truly special is their consistency. Because they all explode at roughly the same mass, they reach nearly identical peak brightness. This predictability has earned them the nickname standard candles in astronomy. Scientists use them as cosmic measuring tapes, calculating distances to far-off galaxies by comparing how bright these supernovae appear to how bright they should be. In fact, it was observations of Type Ia supernova that led to the groundbreaking discovery of dark energy, the mysterious force accelerating the universe's expansion. So while they may lack the brute force of a core collapse supernova, Type Ia explosions are precision tools in the astronomer's toolkit, and proof that sometimes even the smallest stars can leave the biggest mark. Now let's step into the aftermath of these colossal explosions. When a supernova erupts, it doesn't just vanish, it leaves behind a chaotic, beautiful fingerprint on the cosmos. Picture this, a vast, glowing cloud of gas and dust hurled outward at unimaginable speeds. These are supernova remnants, the cosmic debris fields that tell the story of a star's final act. Take the Crab Nebula, for example. This swirling, filament-filled spectacle is the leftover wreckage of a supernova observed here on Earth in the year 1054. Even now, nearly 1,000 years later, its shockwaves are still racing through space at over 1,500 kilometers per second. But these remnants aren't just pretty cosmic fireworks, they're celestial recycling plants. As the shockwaves plow through interstellar space, they compress nearby gas and dust, creating dense pockets where gravity can take over. These collapsing clouds become the nurseries for new stars, kickstarting the cycle of stellar birth all over again. And here's the real kicker: supernova remnants are cosmic alchemists. The intense heat and pressure of the explosion forge elements heavier than iron, gold, platinum, uranium, and scatter them across the galaxy. That gold ring on your finger, it was likely forged in the heart of a dying star and blasted into space by a supernova remnant like this. So while the explosion itself lasts mere moments, its legacy endures for millennia, shaping galaxies, birthing stars, and even sprinkling the building blocks of planets and life across the universe. Now let's turn back the clock and explore how humans have witnessed these cosmic fireworks throughout history. Long before telescopes, people gazed up at the night sky and recorded sudden, brilliant lights where none had been before. One of the most famous examples is the supernova that created the Crab Nebula, which exploded in the year 1054. Chinese astronomers called it a guest star, noting its visibility even during daylight for nearly a month. Imagine their awe as this strange new light outshone everything except the sun and moon. Half a world away, Native American petroglyphs in the American Southwest may also depict this same event, with rock carvings showing a star next to a crescent moon matching the position of the supernova when it appeared. Fast forward to the year 1572, when another brilliant supernova stunned observers across Europe and Asia. Danish astronomer Tycho Brahe meticulously documented its brightness and position, proving it was far beyond the moon, a revolutionary idea at the time. His records helped shatter the ancient belief that the heavens were unchanging. These historical accounts aren't just curiosities, they're time capsules that help modern astronomers track the remnants of these explosions and measure how they've expanded over centuries. From ancient star maps to royal court diaries, humanity's fascination with these new stars reveals something profound. Even without modern science, our ancestors recognized these events as something extraordinary, etching them into memory as celestial marvels. Now, shifting our gaze closer to home, let's tackle a question that might send a chill down your spine. Could a supernova ever pose a threat to life on Earth? The answer lies in the delicate balance of distance and cosmic timing. While supernovae are undeniably powerful, their danger diminishes rapidly with space. For a supernova to harm Earth, it would need to explode within about 50 light-years of our planet. At that range, the blast of radiation gamma rays and X-rays could strip away our ozone layer, leaving us exposed to deadly solar and cosmic radiation. But before you worry, let's put things in perspective. The closest star capable of going supernova in the foreseeable future is Betelgeuse, the red giant in Orion's shoulder. It's around 640 light-years away, far enough that its eventual explosion would be a spectacular light show, not a doomsday event. In fact, some scientists speculate that past supernova might have left subtle marks on Earth's history. One controversial hypothesis suggests a supernova around 2.5 million years ago could have contributed to the Pleistocene extinctions, triggering climate shifts by bombarding the atmosphere with cosmic rays. Evidence like traces of iron-60 isotopes in ancient seabed layers hints at such an event, though the full impact remains debated. The universe is vast, and while supernovae are cataclysmic, their threats are rare and remote. Instead of fear, they inspire awe, reminding us of our place in a dynamic, ever-changing cosmos. And speaking of cosmic dynamism, let's turn our attention to how these explosions have ignited imaginations far beyond the realm of science. Now, let's step into the world of imagination, where supernovae aren't just cosmic events, they're blockbuster spectacles. Hollywood has long been obsessed with the raw power of these stellar explosions, often bending the rules of physics for the sake of drama. Take Star Trek, for example, where starships routinely outrun supernova shockwaves like they're evading traffic. In reality, the energy released would vaporize anything within light years, but hey, where's the fun in accuracy? Then there's Interstellar, which nails the eerie beauty of a collapsing star, but takes creative liberties with time dilation near Gargantua's black hole. But let's be honest, sci-fi's flair for exaggeration is part of the charm. Supernovas symbolize ultimate destruction and rebirth, making them perfect metaphors for storytelling. Anime like Gurren Lagann weaponizes supernova as literal attacks, while Doctor Who turns them into time-bending paradoxes. Even the Avengers got in on the action, with Thanos casually hurling a moon, okay, fine, a dwarf planet, as if it were a supernova's opening act. Of course, scientists might cringe at the oversimplifications, but pop culture's role isn't to teach astrophysics, it's to spark wonder. These exaggerated portrayals invite audiences to ask real questions. Could a supernova power a civilization? What if we could harness that energy? By blending spectacle with curiosity, movies and shows become gateways to deeper cosmic conversations. And speaking of cosmic mysteries, let's shift gears to how scientists actually detect these explosions. No Hollywood special effects required. Now, shifting from the silver screen to real-world science, let's uncover how astronomers actually spot these cosmic explosions. Unlike Hollywood's dramatic flair, detecting a supernova requires cutting-edge technology and a bit of patience. One of the first clues often comes from neutrinos, those ghostly particles that slip through space almost unnoticed. When a star's core collapses, it releases a flood of these particles hours before the visible explosion. Detectors like Supernova and in Japan can catch them, acting as cosmic early warning systems. Then there are the telescopes, our eyes on the universe. Ground-based observatories scan the skies nightly, hunting for sudden bright spots. But space telescopes like Hubble and the James Webb Space Telescope take it further, peering into distant galaxies with unmatched clarity. They capture the aftermath in stunning detail, from shockwaves rippling through gas clouds to the birth of new elements. But here's the cool part: you don't need a PhD to join the hunt. Projects like Zooniverse's Supernova Hunters let everyday people sift through telescope data online, helping professionals spot potential explosions. It's a reminder that science isn't just for experts sometimes. The next big discovery could come from your laptop. And speaking of discoveries, let's dive deeper into one of supernova's most elusive messengers, neutrinos, the universe's silent alarm bells. Now, let's pull back the curtain on one of nature's most mysterious messengers, neutrinos. These tiny, nearly weightless particles are the universe's ultimate escape artists, slipping through matter like ghosts through walls. When a massive star's core collapses, it doesn't just explode outward. It sends a pulse of neutrinos racing ahead of the light, giving scientists a sneak peek hours before the fireworks begin. Take supernova 1987A, the closest stellar explosion we've witnessed in modern times. Hours before telescopes caught the first glimmer of light, detectors on Earth picked up a sudden spike in neutrinos. It was like getting a text message from the cosmos before the party even started. These particles don't just hint at a supernova, they carry secrets about the dying star's core, from its temperature to the violence of its collapse. What makes neutrinos so special? For one, they're born in the heart of chaos. As a star's core implodes, protons and electrons get crushed together, forming neutrons and releasing a flood of neutrinos. And because they barely interact with matter, they zip straight out of the star at nearly the speed of light, untouched by the maelstrom behind them. That's why detectors like IceCube in Antarctica or Japan's Supernova and are so crucial. They're like cosmic eavesdroppers, catching whispers from events billions of light years away. But here's the twist: neutrinos aren't just bystanders, they actually help power the explosion itself. As they flee the collapsing core, they dump energy into the star's outer layers, giving the supernova the final push it needs to blow itself apart. It's a reminder that even the smallest players can have the biggest impact, and that the universe loves a good plot twist. Up next, we'll see how these explosions don't just destroy stars, they're also the ultimate cosmic factories, forging the very elements that make up our world. Now, let's step into the cosmic workshop where the universe's most precious elements are forged. Supernova aren't just about destruction. They are the ultimate alchemists, transforming stardust into the building blocks of planets, jewelry, and even life itself. Here's how it works. Inside a star, fusion creates elements like helium, carbon, and oxygen, but things stop at iron. Iron is a party pooper. It absorbs energy instead of releasing it, so fusion can't go further. But when a supernova explodes, it unleashes unimaginable heat and pressure, along with a flood of free neutrons. These neutrons crash into atomic nuclei like a cosmic stampede, building heavier elements in seconds through what's called the rapid neutron capture process, or R process. Picture this: a single atomic nucleus gets bombarded by neutrons so fast it can't even decay between hits. It's like trying to eat 100 pizzas in one sitting. You just keep piling on until you're stuffed. This creates unstable, overweight atoms that later decay into stable treasures like gold, platinum, and uranium. Without supernova, your wedding ring or smartphone circuitry wouldn't exist. But the story doesn't end there. The explosion flings these newly minted elements into space, where they mix with gas clouds and eventually form new stars, planets, and even us. Every atom of gold in your jewelry was once part of a star's final, fiery breath. And here's the kicker: supernova aren't the only cosmic forges. Colliding neutron stars, another explosive event, also create heavy elements through the R process. In 2017, scientists detected gold and platinum in the aftermath of such a collision, proving the universe has more than one way to mint its riches. So next time you hold a piece of jewelry or marvel at a sunset's colors, remember, you're holding stardust sculpted in the heart of an explosion that died billions of years ago. Up next, we'll explore how some of these violent deaths leave behind something even stranger: black holes, where the rules of physics as we know them break down completely. But sometimes the universe has a different ending in mind. Not all supernova leave behind glowing remnants or neutron stars. Some stars meet a far more mysterious fate. They vanish into the darkness, becoming black holes. When a truly massive star, we're talking at least 20 times heavier than our Sun, reaches the end of its life, its core collapse is so extreme that not even neutron degeneracy pressure can stop it. The core keeps squeezing inward past the point of no return until it forms a singularity, a point of infinite density where gravity is so strong that not even light can escape. That's how a black hole is born. Now, here's where things get eerie. Some stars skip the fireworks entirely. In what astronomers call a failed supernova, a massive star's core collapses straight into a black hole without the dramatic explosion. One moment the star is there, shining in the night sky. The next it's gone, swallowed by its own gravity. Telescopes have actually caught this happening. In 2008, a star 25 times the mass of our Sun simply winked out of existence, leaving no trace except a faint infrared glow, likely the last whispers of dust heated by the newborn black hole's pull. These silent collapses remind us that black holes aren't just sci-fi monsters, they're real cosmic phenomena, the universe's way of erasing a star without a sound. But don't worry, even these invisible giants leave clues. Their gravity bends light, distorts space, and sometimes, if they're snacking on nearby gas, they belch out X-rays that telescopes can detect. So whether it's a dazzling supernova or a star vanishing without a trace, death for a massive star is never dull. Up next, we'll meet another bizarre remnant of stellar explosions, pulsars, the lighthouses of the cosmos, spinning at mind-blowing speeds and beaming radiation across the galaxy. Now, let's turn our attention to another incredible cosmic phenomenon born from the ashes of a supernova: pulsars. These aren't just any remnants, they're the universe's own lighthouses, spinning at dizzying speeds and sending out beams of radiation like cosmic searchlights. When a massive star explodes, its core doesn't always collapse into a black hole. Sometimes the remaining material is squeezed into an ultra-dense ball called a neutron star. Picture squeezing the entire mass of our sun into a city-sized object. That's how compact these things are. But here's where it gets wild. Some neutron stars rotate incredibly fast, some hundreds of times per second, and as they spin, they emit focused beams of radio waves, X-rays, or even gamma rays. When these beams sweep across Earth, we detect them as rapid, rhythmic pulses, hence the name pulsar. Take the Crab pulsar, for example. This cosmic powerhouse sits at the heart of the Crab Nebula, the remnants of a supernova observed back in the year 1054. The pulsar spins about 30 times every second, and with each rotation, it sends out a beam of radiation so precise that astronomers use it like a celestial clock. It's also ridiculously energetic, powering the entire nebula around it, making the Crab one of the brightest objects in the night sky. What's truly mind-blowing is how these pulsars form. During the supernova explosion, the star's core collapses so violently that its magnetic field gets amplified to insane levels, trillions of times stronger than Earth's. This, combined with their rapid spin, turns pulsars into some of the most extreme objects in the universe. They're not just dead stars, they're cosmic dynamos, proving that even in death, a star can light up the cosmos in ways we're still trying to fully understand. Up next, we'll venture beyond our galaxy to explore how supernova in distant corners of the universe help us map the expanding cosmos, revealing secrets about dark energy and the fate of everything we see. But supernova aren't just spectacular events in our own galaxy. They light up the cosmos far beyond the Milky Way, offering us a window into the vast, expanding universe. One of the most fascinating examples is Supernova 2014J, which exploded in the galaxy Messier 82, located about 11.5 million light-years away. When it was discovered, astronomers around the world trained their telescopes on it, capturing one of the closest and brightest type Ia supernova in decades. Studying supernova in other galaxies isn't just about witnessing cosmic fireworks, it's a crucial tool for measuring the universe itself. Because type Ia supernova explode with a predictable brightness, scientists use them as standard candles to calculate distances across space. By comparing how bright these supernova appear from Earth to how bright they actually are, astronomers can measure how far away their host galaxies lie. This technique has revolutionized our understanding of the cosmos. In the late 1990s, observations of distant type Ia supernova revealed something shocking. The universe isn't just expanding, it's accelerating. This discovery led to the theory of dark energy, the mysterious force pushing galaxies apart faster and faster. Without extragalactic supernova, we might never have uncovered this cosmic mystery. Beyond mapping expansion, these far-off explosions also help us study how stars die in different galactic environments. Some galaxies, like Messier 82, are stellar nurseries with frenzied star formation, while others are quiet and aging. By comparing supernova across these varied settings, scientists piece together how a star's surroundings influence its explosive end. So the next time you gaze at the night sky, remember somewhere out there, a star in a distant galaxy is reaching its spectacular finale, lighting up the darkness and helping us unravel the secrets of the universe. And speaking of cosmic mysteries, let's dive deeper into how these explosions shape the very fabric of space and time coming up next. Now, let's shine a light on one of the most telling clues supernova leave behind, their light curves. These aren't just simple flashes in the cosmic dark. They're detailed diaries recording how a supernova's brightness changes over days, weeks, even months. And just like fingerprints, no two types of supernova leave the same pattern. Take type Ia supernova, for example. Their light curves are the gold standard of predictability. After the initial explosion, their brightness spikes rapidly, then fades in a smooth, steady decline. This happens because the explosion burns through a white dwarf's carbon and oxygen at a consistent rate, like a perfectly timed cosmic firework. It's this reliability that makes Type Ia so valuable for measuring distances across the universe. But then there's Type Roman II supernova wildcards of the stellar explosion world. Their light curves are anything but uniform. Instead of a clean decline, they often plateau or even hiccup in brightness. Why? It all comes down to their hydrogen envelopes. When a massive star explodes, the outer layers of hydrogen gas stick around for a while, absorbing energy and re-emitting it in unpredictable ways. It's like wrapping the explosion in a cosmic blanket that smothers and reshapes the light we see. These differences aren't just academic. By studying light curves, astronomers can instantly classify a supernova millions of light years away. Type Ia's tidy curves signal a white dwarf's demise, while Type Roman II messy patterns point to the violent end of a massive star. And sometimes the curves reveal surprises like faint, slow-moving supernova that challenge our understanding of stellar death. So the next time you see a graph of a supernova's fading light, remember, it's not just data. It's a story written in photons telling us how stars live, die, and reshape the universe. And speaking of reshaping, let's turn our attention to how these explosions don't just light up the cosmos. They might hold the key to its darkest secret. Now, here's where supernovae do more than just dazzle. They unravel one of the universe's greatest mysteries. Back in the late 1990s, astronomers made a discovery that turned cosmology upside down. They were using Type Ia supernova as cosmic yardsticks, measuring distances to far-off galaxies when something bizarre caught their attention. These explosions weren't just fading predictably, they were dimmer than they should have been. That meant the universe wasn't just expanding as we'd thought for decades. It was accelerating, pushing galaxies apart faster and faster over time. The culprit. A mysterious force we now call dark energy. Think of it like an invisible hand stretching the fabric of space itself. And Type Ia supernova were the perfect witnesses. Their consistent brightness let astronomers compare distances across billions of light years. Without them, we might never have spotted this cosmic speed-up. The discovery was so groundbreaking, it snagged the Nobel Prize in Physics in 2011. But dark energy isn't just a trophy on science's shelf. It makes up about 68% of the universe's total energy, dwarfing everything from stars to black holes. And here's the wild part: we still don't know what it actually is. Is it a property of space itself, or some exotic particle we haven't found yet? Every new Type Ia supernova we study chips away at the puzzle, helping us test theories and refine our models. So next time you hear about a distant star exploding, remember, it's not just a flash in the dark. It's a clue in the greatest detective story of all time, one that might finally explain why the universe is running away from itself. And speaking of cosmic puzzles, let's zoom in on how you can join the hunt for these stellar explosions. No PhD required. Now, let's bring the cosmos a little closer to home. Believe it or not, you don't need a giant observatory to spot a supernova. Just a bit of patience, the right tools, and a keen eye. Amateur astronomers have actually discovered dozens of these cosmic explosions, and with today's technology, you could be next. Start with a decent telescope. Something as simple as an 8-inch reflector can do the trick. But if you don't own one, no worries. Apps like Sky Safari or websites like the American Association of Variable Star Observers let you scan the skies virtually, comparing real-time images to spot sudden bright spots. The key is consistency. Supernova pop up where they weren't before, so take notes or snap reference photos of your target galaxy over several nights. Now here's how to tell a supernova from an imposter. Asteroids move, they'll shift position against the stars over hours or days. Variable stars, on the other hand, brighten and dim predictably, often in cycles. A supernova, it appears suddenly, stays put, and fades gradually over weeks or months. If you spot something new and stationary, especially in a distant galaxy, you might just have hit the jackpot. Pro tip: focus on galaxies known for frequent supernova, like Messier 51 or Messier 101. And don't forget to report your findings. Platforms like the International Astronomical Union's Central Bureau for Astronomical Telegrams welcome amateur contributions. Who knows, you might even get credit for discovering the next big cosmic blast. And speaking of discoveries, let's turn our gaze to the stars that could light up our skies any day now. Some of the universe's most famous stellar time bombs are ticking, and their explosions could rewrite the night sky as we know it. Now, let's turn our attention to the ticking time bombs of our galaxy stars that could go supernova any day, lighting up our skies in ways we can barely imagine. Among these cosmic celebrities, two stand out as the most likely candidates for a spectacular explosion in the near future, at least on a cosmic timescale. First up is Betelgeuse, the fiery red shoulder of Orion. This massive star has been acting strangely for years, dimming and brightening unpredictably. Scientists believe it's in the final stages of its life, and when it finally explodes, it could shine as brightly as a full moon for weeks. Imagine stepping outside at night and seeing a second sun in the sky. That's the kind of show Betelgeuse might put on. The best part, it's close enough at around 640 light-years away to give us a front row seat without posing any real danger to Earth. Then there's Eta Carinii, a volatile superstar over 7,000 light-years away. This isn't just one star, it's a binary system where two massive stars are locked in a deadly dance. Eta Carinii has already given us a preview of its explosive potential with a massive outburst in the 1800s, briefly becoming the second brightest star in the night sky. When it finally goes supernova, it could outshine Venus, maybe even rivaling the Moon. But here's the big question: when will these stars actually explode? The truth is, soon in cosmic terms could mean tomorrow or 100,000 years from now. Betelgeuse might be teetering on the edge, but stars don't follow human schedules. Eta Carinii is even harder to predict, with its complex interactions making its fate a true cosmic mystery. One thing's for sure, when either of these giants finally goes supernova, it'll be a once-in-a-lifetime event. Astronomers will scramble to study it, and for a brief moment, everyone on Earth will look up in awe at the violent beauty of a dying star. And who knows? The next supernova we see might just come from one of these celestial titans. Now, while we wait for these cosmic fireworks, let's take a step back in time and explore how ancient civilizations interpreted these sudden bursts of light in the heavens. Long before telescopes and modern astronomy, people looked up at the night sky and witnessed these sudden, brilliant explosions, supernova, without knowing what they truly were. Across different cultures, these mysterious bursts of light sparked awe, fear, and stories that still resonate today. Take ancient China, where astronomers meticulously recorded what they called guest stars, unexpected bright lights that appeared and then faded over weeks or months. One of the most famous was the supernova of 1054, which gave birth to the Crab Nebula. To them, these events were celestial visitors, often seen as omens carrying messages from the heavens. Some were interpreted as signs of prosperity, while others warned of coming turmoil. Halfway across the world, Native American tribes like the ancestral Pueblones may have painted their observations of supernova on cave walls. One striking example is a rock art panel in New Mexico, showing a star next to a crescent moon, a possible depiction of the same 1054 event that Chinese astronomers documented. For these cultures, the sudden appearance of a bright new star could symbolize creation, change, or even the arrival of powerful spirits. In Europe, medieval scholars grappled with these cosmic mysteries too. When Tycho's supernova blazed in 1572, it shattered the long-held belief that the heavens were unchanging. Some saw it as a divine sign, while others, like astronomer Tycho Brahe, used it to challenge old ideas and push science forward. What's fascinating is how these ancient interpretations weren't entirely wrong. A supernova is a kind of celestial battle, a star tearing itself apart in a violent struggle between gravity and radiation. And in a way, these explosions do signal change, scattering the elements needed for new stars, planets, and even life across the cosmos. Today, we understand the science behind these spectacular events, but that doesn't make them any less awe-inspiring. The next time you look up at the night sky, remember, you're part of a story that began thousands of years ago with people just like us gazing in wonder at the same explosive stars. Now, let's shift our focus to something even more extreme: the universe's most energetic explosions, gamma-ray bursts, and their explosive connection to supernova. But what happens when a supernova isn't just a supernova? Imagine an explosion so powerful it outshines entire galaxies in seconds, not for weeks but in a blinding flash. This is where supernova meet their even more extreme cousins, gamma-ray bursts. These bursts are the universe's ultimate fireworks, packing more energy in a few seconds than our sun will emit in its entire lifetime. And here's the wild part: many of them are linked to a special kind of supernova called a hypernova. Think of it as a supernova on steroids. When a truly massive star, dozens of times heavier than our sun, collapses, it doesn't just explode outward. It funnels insane amounts of energy into narrow jets, shooting out at nearly the speed of light. If one of those jets happens to point at Earth, we detect it as a gamma-ray burst. But there's a darker side to these cosmic spectacles. A nearby gamma-ray burst could strip away Earth's ozone layer, exposing life to deadly ultraviolet radiation. Some scientists even speculate that a burst might have played a role in past mass extinctions. The good news: the chances are incredibly slim. The closest stars capable of producing such an event, like Eta Carinae, are thousands of light-years away, far enough to keep us safe. What's truly mind-blowing is how these explosions serve as cosmic laboratories. The same forces that could threaten life also create elements like gold and platinum, scattering them across the universe. So while gamma-ray bursts are terrifying in scale, they're also a reminder of how interconnected we are with the most violent events in the cosmos. Now, let's pull back the curtain on how scientists recreate these colossal explosions, not in space, but inside supercomputers. Now, let's step into the digital realm where scientists don't just observe these cosmic explosions, they recreate them. Supercomputers have become the ultimate playground for unraveling the secrets of supernova, tackling puzzles that telescopes alone can't solve. One of the biggest head-scratchers, the ion asymmetry problem. When a star explodes, why isn't the debris scattered evenly in all directions? Observations show lumpy, uneven clouds of iron and other elements, defying expectations of a perfectly symmetrical blast. This is where three-dimensional simulations change the game. Earlier models, limited by computing power, could only simulate supernova in 2 dimensions, like watching a fireworks display through a narrow slit. But modern supercomputers, crunching millions of calculations per second, now render these explosions in full 3D. The result, a revelation: turbulence deep inside the dying star, like a boiling pot stirred by invisible hands, twists and distorts the explosion. These chaotic motions explain why heavy elements like iron don't just fly outward in a neat shell but get flung in clumps and jets. The breakthroughs don't stop there. These simulations have also uncovered how neutrinos, those ghostly particles we mentioned earlier, play a starring role. As they surge from the collapsing core, they don't just escape quietly. They interact with the star's swirling layers, adding fuel to the explosion's fire and helping to shape its uneven aftermath. It's a cosmic feedback loop, with neutrinos acting as both messengers and architects of destruction. What's truly exciting is how these virtual explosions are closing the gap between theory and reality. When supercomputer predictions match real supernova remnants, like the twisted wreckage of Cassiopeia A, it's a eureka moment. Each simulation is a dress rehearsal for the universe's most violent events, helping us decode not just how stars die, but how their ashes seed the cosmos with the building blocks of planets and life itself. And speaking of cosmic seeds, let's turn our gaze to the next puzzle: how these cataclysms might shape the fate of life beyond Earth. Now, let's take a step beyond our own cosmic backyard and consider the bigger picture. Could supernova hold the answer to one of the universe's greatest mysteries, the Fermi paradox? If the universe is teeming with stars and planets, why haven't we found any signs of alien civilizations? One chilling possibility is that supernova act as cosmic reset buttons, wiping out advanced life before it can spread. Imagine a thriving alien civilization, flourishing for millennia, only to be erased in an instant by a nearby stellar explosion. The gamma rays and radiation from a supernova could strip away a planet's ozone layer, exposing life to deadly ultraviolet radiation. The shockwave might even trigger ice ages or mass extinctions. Some scientists speculate that events like these could explain why the galaxy seems so quiet. Life might arise repeatedly, only to be snuffed out before it can make its presence known. This idea ties into the concept of galactic habitable zones, regions of the Milky Way where conditions are just right for life to survive and thrive. Too close to the crowded galactic center, and the risk of deadly supernova skyrockets. Too far out in the sparse outer edges, and planets might lack the heavy elements needed for life in the first place. Earth, it turns out, sits in a sweet spot, far enough from the chaos of the inner galaxy, but close enough to benefit from its elemental riches. But here's the twist: even within these safer zones, supernova aren't entirely avoidable. Stars like Betelgeuse remind us that danger can lurk relatively nearby. The question then becomes, how often do these catastrophic events occur? Some research suggests that Earth might have been bathed in supernova radiation multiple times in its history, possibly linked to past extinction events. If that's true, then the rise of intelligent life might not just be a matter of time and chemistry. It could also be a race against the next cosmic explosion. So, are we alone because supernova keep hitting the reset button? Or is life more resilient than we think, finding ways to endure even the universe's most violent tantrums? The answer might lie in the delicate balance between destruction and rebirth, a dance of fire and stardust that shapes the story of life itself. And as we ponder these cosmic what-ifs, let's turn our attention to the lingering mysteries that even the brightest minds haven't yet solved. But even with all we've uncovered, supernovas still guard some of their deepest secrets. One of the biggest head-scratchers is why some of these explosions aren't symmetrical. When a star dies, you'd expect it to blow apart evenly in all directions, like a perfectly round firework. Yet observations show many supernovae are lopsided, with debris flying faster in one direction than another. Scientists suspect this asymmetry might be tied to how the star spins or how its core collapses, but the exact mechanism remains a mystery. Then there's the puzzle of Type 1, a supernova. We know these explosions happen when white dwarfs steal too much mass from a companion star, but the details are fuzzy. What exactly tips the scale from a stable white dwarf to a catastrophic blast? Some theories suggest it's a slow buildup of material, while others argue for a sudden merger with another white dwarf. Without a clear answer, predicting these cosmic fireworks is nearly impossible. Upcoming projects like the Vera Rubin Observatory might finally shed light on these enigmas. With its massive telescope scanning the entire southern sky every few nights, it could catch supernova in their earliest moments, revealing clues about their triggers and asymmetries. Other missions, like space-based gravitational wave detectors, might even sense the ripples from a star's final moments before the explosion becomes visible. So while we've come far in understanding these stellar explosions, the universe still has a few cards up its sleeve. Each unsolved mystery isn't just a gap in our knowledge. It's an invitation to keep exploring, to keep questioning, and to stay curious about the violent, beautiful chaos of the cosmos. And as we look ahead to the next chapter in this cosmic detective story, let's turn our gaze to the stars themselves specifically, the ones that might be next to go supernova. As we wrap up our journey through the explosive deaths of stars, let's take a moment to reflect on the incredible role supernovae play in the cosmos. These dazzling explosions aren't just spectacular light shows, they're the universe's ultimate recyclers. Every time a star goes supernova, it scatters heavy elements like gold, uranium, and iron across space, seeding the raw materials for new stars, planets, and even life itself. Without these cosmic detonations, the building blocks of our world wouldn't exist. Supernovae also serve as cosmic mile markers, helping astronomers measure the vast distances of our expanding universe. Type 1 explosions, with their predictable brightness, have been crucial in revealing the mysterious force of dark energy, proof that these stellar explosions are more than just fireworks. They're tools for unlocking the universe's deepest secrets, so the next time you look up at the night sky, remember, every twinkling star has a story, and some are destined to end in a blaze of glory. Whether it's Betelgeuse looming in Orion or a distant supernova waiting to be discovered, the cosmos is alive with explosive potential. If you've enjoyed this dive into the life and death of stars, don't forget to hit that like button and subscribe for more mind-blowing space content. Turn on notifications so you never miss an update, and let us know in the comments which supernova mystery fascinates you the most. Until next time, keep gazing upward and wondering about the incredible universe we call home.